So, curved arrow mechanism. Sorry to interrupt your conversation. Curved arrow mechanism for the formation of the reaction product. I guess we'll look at the first attempt. Um, so first and foremost, what do you think is interesting about the mechanism as shown? No, just overall. I guess we could say initial impressions, maybe. As soon as I get a marker up here, I can try and remove some of this stuff. Yeah, like if I get rid of all this. Okay. So a nucleophile is attacking a nucleophile. When we've talked about the aromatic ring, we've talked about it almost exclusively as a nucleophile. It's got all those pi electrons. We would expect it to act as a nucleophile. So if we go through and look at the oxygen, we're showing the oxygen also being a nucleophile because it has that lone pair of electrons. Typically also when we're looking at our aromatic rings, we're looking at EAS, electrophilic aromatic substitution, which is the electrophile substituting for what on the aromatic ring? I know that was a lot real fast. What is the electrophile substituting for on the aromatic ring? It's a hydrogen. So we're exchanging a hydrogen for whatever our electrophile is. And if we look to the very end in our locked box, so it's locked, so we know that has to be the end. If we go back to the beginning, what changed? Okay. And we'll be careful with the word electrophile because the oxygen doesn't make sense to be an electrophile. Okay, but it looks like what we're doing is substituting the bromine for another atom structure. So this doesn't fit the EAS mechanism, and that's because it's not EAS. Okay, we could take a step back and say, well, when we look at aromatic rings, we would say they would act as nucleophiles, they're electron rich. There's no way we would expect them to act as electrophiles. That just doesn't make sense. In the instant we make that statement, what does somebody have to do? Not just test it, they have to break it. Okay? And so someone went through and was able to verify that you can make an aromatic ring act as an electrophile. To act as an electrophile, what charge does the aromatic ring need to be? Our aromatic ring would need to be positive to be an electrophile. So when we look at that starting structure, what characteristics or what things are on that structure that would help me to say that it is acting as an electrophile? We need to see a positive charge. I don't have an explicit positive charge there, but what we're trying to look for is building positive charge. Electron withdrawing group where? Okay. So I want to lean in that a little bit. The NO2, I actually want to say it's not NO2 that is our electron withdrawing group. Okay, we should be much more specific. It's not NO2, it's just the nitrogen. It's that positive nitrogen that's going to act as an electron withdrawing group. It just so happens it's becoming positive because it's also connected to those oxygens. So we've got an electron withdrawing group in the nitrogen. Arguably, we also have an electron withdrawing group in the bromine. Okay, so we've put effectively two electron withdrawing groups on the ring. What is that going to do to the electron density in the ring? Decrease it. Okay, it's going to decrease it enough that theoretically we could make it act as an electrophile. Kind of, sort of. If we were now to go through and say, well, where would I expect it to be electrophilic? Which positive is more positive? The positive where our bromine is located. Whoa. Still not used to the patterns that I'm trying to draw. The positive where the bromine is located or the positive where the nitro is located? Yeah, I would argue the nitro is more electron withdrawing, which means to me, I would say the positive or the nitro is the more likely place to attack. Okay? So that would suggest our oxygen with its lone pair of electrons could now share with that positive. The problem with that is if we were to draw that out, how could we stabilize that structure? Because we would lose aromaticity, just like with EAS. So we've got our NO2, we've got our oxygen with the hydrogen, still a lone pair on it. That bromine's there. We're going to take our electrons from the pi bond, shuttle them up, so we'd be looking at a lone pair on that carbon. We still have this, we still have this. Okay, and I want to effectively reform aromaticity. To reform aromaticity, what would I have to do? I would have to bring those electrons back down to restore aromaticity. But in that restoration of aromaticity, I would exceed the octet on that carbon, right? So I would have to eject, now my green carbon, I would have to eject a leaving group. Ignore for the fact that that oxygen is positive for the moment. Is NO2 going to be a good leaving group? It withdraws electrons into itself, meaning it keeps them inside itself. NO2 is a trash leaving group. There's no real good way to stabilize that charge. Which ultimately means, what are we going to eject? The nucleophile that just attacked. Okay? And so this largely has to do with leaving group abilities and how it can actually establish and stabilize those structures. Okay? So if it didn't attack there, where could it attack? At the carbon site with the bromine, which would shuttle the electrons the other direction. If we set this up as kind of a color-coded system, figure out where I'm at. We've got our nitrogen. Hopefully all that's being shown. There's a crap ton of arrows making this hard for me to even track. Green bond to our oxygen, hydrogen. So far so good. Positive, and we'd have the lone pair electrons there, right? So if we're considering what could happen, both of these two states are going to be our possibilities. Okay, we said we didn't like NO2 as a leaving group, okay, because we wanted to restore aromaticity. If we go up and look at our green structure, we still want to restore aromaticity, but is there something extra special about this structure? This green structure has the ability to do resonance into that nitro. So the product of our oxygen attacking the carbon where the bromine is produces a more stable intermediate than if the oxygen attacked the carbon where the nitro was. What does that suggest? The top pathway is going to be our correct pathway. Okay, so we get that resonance stabilization that helps us out. Add to it, since we're not being asked for that resonance in this question, what could those electrons potentially do? They could crash back in. We would exceed the octet, now I'll call it our red carbon. And if that's now exceeded, what would he have to do? Kick out a leaving group. Do I have a leaving group? Bromide's a pretty good leaving group. Okay. For the sake of mechanisms and trying to answer the question all the way through, which is the better leaving group, the oxygen or the bromide? If the oxygen leaves, what does it leave as? Does it leave as a negative? No, it leaves neutral. If the bromide leaves, it leaves as? Which one's the better leaving group? The neutral one. So what does that mean? While I like to restore aromaticity, if I did the restoration of aromaticity, all that's going to happen is I'm going to reverse the reaction. So first, what we would need to go through and do is address the instability of the positive charge on our oxygen if we're going to try and progress forwards. So we're going to leave the negative alone for the moment. We'll take We'll take electrons away from the hydrogen bond. This propagates us forward just a step. Positive, lone pair, lone pair. We still have the negative charge on our oxygen. Our bromide, our oxygen up here. Now with an extra lone pair. And now what can happen? Now we can resonate those, or not resonate, but move the electrons from our negative carbon in to kick out a leaving group, which is now the better leaving group, bromide or oxide. Bromide, why? The larger size is what's keeping that more stable as a leaving group. We restore aromaticity. And I'm just going to write that as NO2 in this case. So far, so good? Okay. If we backtrack this through the number of boxes that we would predict, we would have got our starting box, okay, which we could clean up here because we don't want red arrows in there. We only want to see those green arrows. So that would take us to our first box. Okay, that's really ugly to erase. That first box matches this structure directly above it. I know that's showing a resonance arrow. That's not a resonance arrow. Second box for that one. And then the third box for the end. Make sense? Everybody good with everything that is written in there? I think so. Yes, so I believe I see what you're saying. You're not talking sigma structures. What you're talking there is that we're using the pre-resonance, if you will, to dictate where our chemistry is going to fall. So that if we looked at that starting structure with our nitro, there's our bromine, and we want to understand, and actually I'm going to do this. I'm going to erase the bromine. That if I have that nitro on there with that positive charge, how is it going to control how this structure could act as an electrophile? Okay, well, it's going to control through resonance, right? Our pi electrons could shuttle out. Where does that build a positive charge? Oops. I sort of got it right and then sort of didn't all at the same time. I'd build a positive charge there. That's not our para, that would be our second position or our ortho. If we continue to do our resonance, we could get it around to the para position. Yeah, and if we continue to do resonance, we could get it around to the other ortho position, right? So what I believe you're asking is, could we use those resonance structures to help us predict where it would be electrophilic? Yes, but we also have to leverage this a little bit more. When we're doing this electrophilic reaction, what are we substituting? And this is exactly the issue that I wanted to point out. When we ran this reaction, are you substituting a hydrogen? No, what you're substituting for is the bromine. Okay, so by looking at these resonance structures, what we're establishing is that if I want to run an NAS reaction, where does the bromine need to be relative to my electron withdrawing group? I need to make sure that when I run my reaction, I need my bromine at any one of those positions. What if it's not at one of those positions? Then it's likely to not happen. The substitution isn't aligned in a favorable situation that would allow for resonance stabilization of your intermediates. How would you be able to predict that? Well, start with the meta substitution, draw out this mechanism. Do you see a resonance stabilization coming out of it? And what you'll find, sorry, just talk to me. What you'll find is you don't get that extra resonance stabilization. And without that resonance, you can't propagate that reaction well. Kind of, sort of?
So it's like we can kind of establish by rote which is the better electron withdrawing group in this case, and then we can just say this is the one that's controlling the reaction, and the bromine is secondary.
Yeah.
Just like forcing that position.
So if we were to look at this starting structure, how do we know we should be looking at this and be thinking NAS versus EAS?
Since we have two electron withdrawing groups, it's likely to.
Consider the magnitude of the charge building within the ring. For the record, the recording is going to die out and we're going to lose audio because of the headphones are saying, charge me, charge me. Just so you all know. So if we're looking at that starting aromatic structure, I have electron withdrawing groups. That's going to make my aromatic ring electrophilic, which means I can't do EAS. I have to do NAS. If I look at that starting structure and it has maybe only one electron withdrawing group, then maybe I can consider EAS. Even then, if I have an electron withdrawing group on it, what's going to happen to the rate of the EAS reaction? It's going to be slower, so that's not a favored situation. Likely to not see that. That would not be a preferred path. Kind of, sort of? Okay. Good follow-on question. Didn't answer my question, but that's okay. Are we good with everything that's drawn up there? Yeah? You entered into smart work, you're wrong. Everything that I drew. Don't worry about the boxes underneath necessarily, because the boxes underneath actually fix some stuff. Did they set it up that way? They did. I would disagree with that. They may have it set up to run both directions. Oh, yeah, they may have it set. Oh, yeah, they did do it the other way. They swapped the order of those two. I think that's a mistake. There's an extra piece behind it. When they lost that hydrogen, How did I show it? I just showed one arrow. I just showed the electrons from that bond going to the oxygen. Why is that problematic? I would have H plus in solution. This comes down to different mechanistic discussions, and arguably you can already see different mechanistic discussions on which piece should happen first. Okay? Their argument here, or the argument that they're trying to make, is that you can't just have a bond break. Bonds don't just break. Something makes them break. Okay? To me, anything that's basic in solution is going to cause that bond to break. So I don't care to specify it. Did they want you to specify it here? Yeah. That's why that second molecule is appearing. They want you to show that those electrons are picking up that hydrogen. Everybody see that? I would argue the sequencing is wrong based off of leaving group abilities. Okay. You're forced into the sequence they gave you. Because if we wanted to do the deprotonation first, we don't have the base to remove it, which is why we have to change the order around. Everybody see that? Feel confident you can get it right and entering it in SmartWork? Okay. What next? Oh, actually, what next was the next question on the thing, right? You said you tried it. See if it'll attempt. Cool. I think all you had to do was look at it. You didn't have to actually submit, for the record. So, in this case, nucleophilic aromatic substitution reaction of halobenzene with a strong base involves benzyne intermediate. Okay, so if we're going through and evaluating this structure, we now want, again, curved arrow notation. Let's take a look at that starting material. Whoops, I gotta do my buttons. Just curved arrows again. We'll erase that one bond. Based off of what I'm seeing, I'm gonna bet that one of your steps was that you needed to include lone pairs. Okay, so that would be something you'd need to fix in each of these. If we take a look at that starting material, what jumps out to you? Okay, we have a base. We know it's a negative nitrogen, which means we should be making sure to add our 2 lone pairs. What else is up with that? Did you tweak it? No? Okay. Just curious.
The hydrogen right there is not viable. Makes it seem like it's
Okay. So really long bond on the chlorine. Seems a little weird, a little suspicious. Why is that long? We're also seeing that hydrogen being explicitly stated. Both of those, what you're attempting to do is kind of logic through why these steps were made. You're trying to think through why would they give me this information in this format. Okay. You will do similar things when you get to a test. Why is this information given to me? Are they trying to lead me somewhere? Okay, that's fair. Where I was asking you is when we look at that starting material, should it do EAS or NAS? Actually, we can do it this way. Look at the second box. Only the second box. Should that do EAS or NAS? Why NAS?
Because our ring is acting as like chlorine. That's
Okay, I like where you shifted on that. The acting gets me nervous because acting is now saying you're looking at the full reaction. I said, we're not looking at the full reaction. I only want you to look at that structure. Right? So only looking at that structure, you could say, well, chlorine is electron withdrawing. Is it a strongly deactivating group that's going to make that aromatic ring want to act like an electrophile or a nucleophile? No. Okay? So this particular substrate, if anything, is more susceptible to an EAS reaction. We'd be looking at this and saying this is probably going to run ortho-para substitutions around the chlorine because the chlorine, even though it's deactivating, is a para-ortho director. Yeah? Okay. So if that's our initial assessment in looking at that structure, what would I expect to see as the reagent mixed with said structure? I would expect to see an electrophile. So if I go through and start to erase all these pieces so that we can see them again, why should we immediately be like, well, wait a second, when we look at the reagent being mixed with it? Because I actually wouldn't go that far. It's not wrong, but it's electron dense. And what's the issue with electron dense? It would not want to be an electrophile. That's all I'm trying to get you to draw as a conclusion. Okay, kind of makes sense? So then, what could it do then? Okay, and if you didn't know, I wouldn't blame you because this is goofy. This is one I'm actually surprised we don't teach it as a named reaction. I'm sure it is a named reaction. I honestly don't know what it is. Okay. With that being a strong negative, we need to find something positive. It doesn't really make sense to do a nucleophilic attack on that ring because the ring we would expect again to be a source of electrons, so that doesn't really make a whole lot of sense. We could go through and look at the rest of the mechanism. The very next step doesn't make it look like we do anything with the chlorine, right? So if we're not going to react with the chlorine, what do we need to react with? So let's take those electrons and react with the hydrogen. The hydrogen has now exceeded its octet, which means we need to push the electrons. We want to push the electrons the shortest distance possible, so we'll push them onto the carbon. What would our resulting structure look like? We did nothing really to the vast majority of our carbons. We do add a lone pair on that carbon. We didn't do anything to the chlorine. But since we now have a lone pair on that carbon, we could say nucleophilic, but we're trying to finish the drawing first. It's negatively charged. Okay. For the sake of smart work, I just happen to remember that we were drawing lone pairs. Don't forget your lone pairs up on your chlorines as we navigate through. Okay. Getting a negative on the ring seems kind of weird, but hey, that's where we're at. What might we predict from here? Okay. Again, in a vacuum with no other context, I would expect you to predict absolutely nothing. Okay. This is bizarre and weird. Okay. What's happening is we can look to our product. Okay. This is a mechanism question. You're being asked to show curved arrows. So add curved arrows to make it look like the product. Okay. So if we're looking at our benzene structure, what happened? I have a new pi bond. To do a new pi bond, what has to happen? An elimination. I need a leaving group to leave and my pi bond to form. So I'll take that negative charge, swing that in to make my pi bond. I exceed the octet on that topmost carbon, and now I can eject the chloride. If we're going to look at the product of that, the chloride should now have our 4 lone pairs. Or sorry, yeah, I said that right. 4 lone pairs. There should be no charges or lone pairs on that, I'm going to call it benzene structure. Does that benzene structure look weird? Yeah? Why? It's got a triple bond on it. Have we talked about things like that before? Can we have a triple bond in a ring structure? We said no. We've actively said no for a long, long time. We would say that that doesn't make sense. Why does that not make sense? The bond angle between those two green things, those two green bonds in my crude drawing, need to be 180 degrees. To get it to be 180 degrees, that doesn't seem physically possible. Okay? And if it's not physically possible, then shouldn't happen. Okay? So we'll ignore that for the moment because maybe someone's just pulling a rude prank on us. So if we've got this structure set up as it is, we want to finish out that box. We want to make sure we get our lone pairs. We still have more of that negative nitrogen floating around. Okay, what could we do now? How do you know the negative nitrogen needs to act as a nucleophile?
Because so the nitrogen could be a nucleophile and
Easier. Why is the negative nitrogen going to act as a nucleophile? Okay, we know the nitrogen is involved in making a bond. Great. So the nitrogen has to be nucleophilic or electrophilic. Why do I know it needs to be nucleophilic? Lorraine, would you say? It's fucking negative charge. Okay? That's screaming at you, I need to stabilize that negative. Okay? That's why it's the nucleophile. So you're not wrong, because easier answer.
Yeah.
Okay, it's negative. So that negative needs to find a positive. Where is there a positive? I would argue this is an equally challenging question because the chloride's clearly negative. We could look at the benzene structure. We said the benzene acts as a nucleophile on the best of days as a benzene, and I frickin' put an extra pair of electrons on it. Shouldn't it be wickedly negative? Yes. But it's not formally negative. So let's just have this come in. And if it comes in, what happens to that carbon? It exceeds the octet. I need to shuttle the electrons up to the other carbon. Why did I have it attack the bottom carbon and not the top carbon? Number one, doesn't matter. Why did I do it? Because when I look at the next image, it looks like it's aligning there. So there's that new bond. Okay, I didn't react one of those lone pairs. And then when I broke that other pi bond, I shuttled another lone pair up there. Before I continue on, I've got to make sure I've drawn a proper structure. Do I have a proper structure? I haven't even, I'm not worried about the nitrogen yet because I need to make sure that I've drawn a proper structure first. I need a negative charge. Now I could go through and say, well, do I need to continue or do I need to finalize this? Well, first off, should we continue? Yeah, why? There's another picture, awesome answer, and I've got a negative carbon. We've got charge, we should try and neutralize this. Okay, and in particular a negative carbon. So we're going to want to continue this reaction with whatever else is drawn within this box. This is where we could go through and acknowledge that that thing that was drawn within the box wasn't drawn correctly, and we need to make sure that we get the lone pairs on that. Okay, so now what happens? That negative carbon is going to be my source for my arrow, and it needs to reach out and find something positive. Where's there something positive? The hydrogen is positive because I don't like, you're not wrong, I don't like weak acid as an answer because it's something you've memorized. When you're right, you're right. What's a better or a Mike better answer? Go back to the properties of the individual elements. Nitrogen is more electronegative than hydrogen, which means all of those hydrogens are partially positive. I can pick any hydrogen I want. The electrons in that bond are going to go to the nitrogen because nitrogen was more electronegative. This establishes my arrow pushing and sets this up. The problem with memorizing it as acid is that as soon as you screw that up, the whole thing crumbles on you.
And well, you have to refund it within the mechanism. So it's like that's also
Refund it in the mechanism?
because in the beginning you started with a base.
True, but we would only have to refund it if we knew it was a catalyst.
Is it not a catalyst?
You tell me, if we take a look at this starting material,
That looks like a.
and I look at this as a, let's just start with this as a temporary product, is that NH2 acting as a catalyst? No, it's actually connected to the structure, so it's not a catalyst, it's actually a reagent.
So then
Could a second equivalent be acting as a catalyst also? That gets a little bit gray, but yes, you could make that argument. It's going to be real hard to say, oh, NH2 is acting as a catalyst. Well, half of it is. Dangerous. Okay. If we finalize that reaction out, we've got our new hydrogen on there. There's the electrons that we used, that lone pair. The lone pair picked up on our nitrogen. And I guess I'll draw the old one as black. And we could go through and draw in our final answer. I know I can't scroll appropriately to see that final structure underneath, but I can tell you what's underneath. We've got a line to a hydrogen down there, right? Are we done? Because it's smart work. SmartWorks being real picky, make sure you get that lone pair on your nitrogen. Should we protonate it? Because every time we've had nitrogen before, we put a stupid hydrogen on it, make it H+. Basic conditions, don't protonate it. Okay, and we'd now have our final answer. Okay, so there's some things that I would like to point out through this. We got to this triple bond and we said, that's stupid. And I said, we're going to talk about it later and we're just going to move on. We're moving on because we're being forced to go through and show this as the mechanism. They're saying these things are happening. We just got to do it. Okay. Now that it's done, we can double back and be like, but really? Did this actually happen? How do we know that this mechanism is actually valid?
would you say in resonance intermediate? I mean, is it actually a triple bond forever? Like
So you could run a couple arguments. You could go through and say, well, it's not actually a triple bond because that triple bond space-wise, I didn't draw the other double bonds in here, just makes this weird tweak in the structure and we don't like that. So we could go through and say that it's actually in a resonance form where it's doubly charged. Oh, you can't have double charges in structures. Yeah, you can. Yeah. You remember the Wittig reagent with the ylids? That had a positive and a negative in it also. So yeah, we can have that double charge. So now it's a question of, well, which do we prefer? Do we want to show it as this neutral with that goofy ass triple bond, or do we want to show it as this double charge thing? Okay. But was it 6 of one, half dozen of the other? Both of those are going to look pretty gross. Okay. And depending on whose camp you're in, you may fight for one argument versus the other on which one's the more appropriate intermediate. Right? I have no dog in this race. I don't care. Okay? But this is the accepted mechanism for this reaction. Again, I would ask, how do we know this is even a reasonable mechanism to be launching into? That's the primary aspect. These aren't just people sitting down saying, you know what, I'm just going to fuck with people and draw whatever I want. That's not how this works. Okay? What happened is they took these reagents, they ran an experiment, and when they ran the experiment, they got products that didn't make sense. This is not one of the reactions that would allow you to see that it didn't make sense. Okay? We could tweak it ever so slightly. And this is not a reaction I'm super comfortable with, so I may be tweaking it in an inappropriate fashion. That sounds very weird. Hopefully the microphone died. Let's just go through and drop a CH3. What's that?
I said YouTube's gonna love this one.
Yeah. I get lots of people. Maybe it's time. Maybe my time to teach is done. Um. What are they going to do? Fire me? Probably. Um, how would this change the dynamic or change the output of our chemical reaction? Okay, and as a hint, that's not the eraser I wanted to use. By adding that CH3, how is this going to change my reaction?
Makes one area more positive. There's a tertiary.
There is a tertiary in there. Is that tertiary going to have an effect? Would we predict that pi bond to do any resonance through the rest of the ring?
So CH3 is an electron donating slim.
Yeah?
I swear I had this same on Tuesday. You were talking about
Does it affect the pi bond?
it is, and it's weird
The
that
pi bond that is gross that we don't like. It's that extra. Yeah, thank you. That's a good term. I like that. Does it affect our, and I did it again. I clearly don't learn my lesson. Go back and just watch all the videos. Is it going to affect that pi bond?
Does it just control the position of the reaction?
So if it's controlling the position of the reaction, you're saying yes, it affects the pi bond. Can that pi bond do resonance with that system? It's entirely outside that system. Which means when I go through and look at the resonance of my gross triple bond structure, I could have drawn the resonance as I did on the left, or I could have drawn the resonance as I have now done on the right. Why does that matter? Nope. What is the nitrogen reacting with? A positive carbon, right? But I just said that triple bond has no resonance with the ring system, which means which carbon is going to be positive?
it doesn't matter because it's identical.
Either, which means two products. I can get the system where our nitrogen comes in and reacts from the bottom, or I can get it coming in and reacting from the top, which means when I look at the output of this reaction, what do I see? I get two products. I get the product where I have the CH3 here and my NH2 there, and, should have written and, oh well. I get the product where I have the NH2 here and my CH3 there. So I get the system where the NH2 is ortho. I also get the product where it is meta. How could I possibly get those two products? Well, really the only explanation that works is that this nitrogen is equally reacting at both those spots. And the only way it can equally react at both those spots is if whatever it's reacting with is outside the effective reactivity of our ring. Yep. Which then means it has to be some external thing. That's suggesting that I'm probably looking at an extra pi bond situation. Okay. What do we know about the reactivity of the pi bonds in aromatic rings? Generally speaking. They're all resonance stabilized, which means They don't react. They have to be forced in EAS reactions, which is why when we went back to the very, very beginning of the semester and we talked about doing reactions with alkenes, we never saw an aromatic ring here, right? No aromatics, because the aromatic ring structure doesn't react with normal electrophile reactions. Okay? And if we push even further back, there were special cases of pi bonds that started to do interesting things like resonance, right? We could have two pi bonds. Those can resonate with each other and they still reacted. Interestingly, we didn't even have to react them with a normal electrophile. We could react them with another pi bond, right? And in both of those cases, they were never aromatic rings. What kind of product did I get here? Cool, this is a Diels-Alder. I get that 6-membered ring, right? I totally drew that in the worst possible way to draw that product, but hey, it's there. I got a Diels-Alder product. If the formation of this triple bond, okay, and let's actually rewind back even a little bit further, we go back to that Diels-Alder, did it have to be an alkene? Did that have to be an alkene? No, it could have been.
A ring, but not a non-aromatic ring.
It could have been a non-aromatic ring. What else could it have been? It could have been an alkyne. The key chemistry within the Diels-Alder was not that we were reacting alkenes, it's that we were reacting non-polar pi bonds and non-aromatic non-polar pi bonds. If this mechanism is true, I'm going to form a pi bond, right? A pi bond that would not be aromatic. And if that structure came into existence, I have a non-aromatic pi bond. Shouldn't it react in a Diels-Alder situation? Because the rules for Diels-Alder were non-aromatic, non-polar pi bond. Well, that's a non-aromatic, non-polar pi bond. So you can say, well, I think this is BS. I don't like it. Even though I got two products, it must be doing something else. So I'm going to throw it into a Diels-Alder situation and see what happens. And what happens? It reacts just like a Diels-Alder reaction should. That gives us even more credence to the theory that we are actually forming this goofy triple bond in the aromatic ring. And because now we have piling evidence explaining why we have a goofy triple bond in the aromatic ring, now people have to go through and say, well, for this 180 degrees, it can't do 180 degrees. So now some really good spatial awareness, three-dimensional manipulation person can go through and play with that shape. And we discovered that there is a way that you can generate the triple bond while still maintaining your aromatic ring. This is going to lose aromaticity. Why does it lose aromaticity? The pi bonds are no longer in alignment, but do we have a shape that allows for that 180 degrees that still allows for all of the atoms in the ring? Yeah. And so when this forms, I could easily have drawn this structure wrong. That felt way too easy and fast. We form this weird death spiral of a structure, and now we can say, okay, maybe this actually makes sense. Okay, we didn't like dealing with the three-dimensional shape first, so we went through all the possible experimental evidence to prove that it came into existence. So why go through all of this? Well, this is really bizarre, crazy chemistry, right? And if it's bizarre, crazy chemistry, what do you think is going to be expected of you? To know that it exists. Okay? So when we talk about the aromatic section of contents, this is our last question, I believe, within the smart work. You're responsible for EAS. The primary reason for our EAS reactions is kind of twofold: resonance, lots of resonance, okay, and then knowing your reagents. Okay, the knowing of the reagents isn't the critical part, it's the order in which you do the reagents to create a particular product. I don't have an easy way of clearing things, so I'll crudely draw it up at the top. So if I start with a benzene ring and I want to make CH3Cl, and oops, that's my eraser, NO2. Well, how do I get a CH3 on a structure? How do I get a chlorine on the structure? How do I get NO2 on the structure?